On behalf of the Royal Swedish Academy of Sciences, I wish you all welcome to the Crafoord Prize Symposium in Geosciences that is held in honor of 2014 Crafoord Prize Laureate Professor Peter Molnar. This symposium is the first of 3 Crafoord days that will continue tomorrow with a prize ceremony in the presence of His Majesty the King. And during the 3rd Crafoord Day, Professor Molnar will deliver his Crafoord Prize lecture appropriately in Lund, which represents the home base for the Crafoord family, which through generous donations have made the Crafoord Prize and Crafoord Days possible. The Anna-Greta and Holger Crafoord Fund was established in 1980, and the first Crafoord Prize was awarded in 1982. And this is an international prize that recognizes groundbreaking research in astronomy, mathematics, geoscience, bioscience, and polyarthritis, a disease that the donor Holger Crafoord was suffering from. The Crafoord Prize in Geosciences has been awarded since 1983, and with Peter Molnar included, 14 geoscientists have been awarded at 10 occasions. The most recent laureate was Professor Walter Munk for his contribution to our understanding of ocean circulation and tides and waves and the role of the Earth dynamics. And the prize motivation for the Academy's Crafoord Prize Committee in Geosciences for Professor Molnar's contribution was for his groundbreaking contribution to the understanding of global tectonics, in particular to the deformation of continents and the structure and evolution of mountain ranges, as well as the impact of tectonic processes on ocean, atmosphere, circulation, and climate. It's therefore appropriate that the title of this symposium is Mountain Belt Dynamics. We are very grateful that this symposium has attracted a full audience here in the Bear Hall, and I'd like to give a special thanks to all the speakers that, despite short notice, have accepted the invitation to participate here today, and they have traveled far. The Royal Swedish Academy has a long-standing engagement in geosciences, including environmental, climate, and energy-related research. One example that we don't discuss often is IGBP, the International Geosphere-Biosphere Program that is housed here at the Academy, that coordinates international research on global scale and regional scale interactions between the Earth's biological and chemical processes and interactions with the human system. And IGBP was involved in the work leading to the IPCC report recently. We have also here the Swedish Secretariat for Environmental Earth System Sciences, SES, that works to promote Swedish participation in international programs. And here we also have the Bayer Institute that is doing research in the interface between natural science, ecology, and economics. The very new Academy program, Global Economic Dynamics and the Biosphere, financed by the Family Erling Persson's Foundation, is up and running since the beginning of this year. And I'm very excited on what these young scientists that are housed here now are going to accomplish. Well, I end here and just inform you that today's Crafoord Prize Symposium is headed by 3 chairs. We have Sten-Åke Elming, David G. and Martin Whitehouse, and all 3 are members of the Crafoord Prize Committee that has been chaired by Gia Destoni, that is also here at the audience. And I now invite Martin Whitehouse on stage. Please, Martin.
Okay, thanks, Staffan. Well, I'd like to, on behalf of the Crafoord Prize Committee, add my own welcome, or our welcome, to all of you today to this symposium on mountain belt dynamics. Before we start the scientific program, I have got a list of practicalities. There's a few boring things we have to go through. So the first of these is that we are webcasting live this symposium. So bear in mind we will have question and answer sessions after each of the speakers. So please wait until somebody hands you the microphone before asking your question. Put your hand up and then somebody will run over with a microphone so that we can make this work with webcasting. We have a very long session this morning. We actually don't have a coffee break this morning. Sorry about that. But do feel free to get up, stretch your legs as you need. We will go until about 12 o'clock. During the later breaks this afternoon, there will be tea, coffee and refreshment available outside. We do have a lunch for the registered participants. It's included in the registration, and you will find some of you should have green dots on your tags, and some have no dots. The people with green dots will actually get lunch in the foyer, just outside the lecture hall here. The people with no dot will have lunch in the Academy Club Villa, which is just across that way. The lunches are exactly the same. There's no segregation. It's just practicalities in terms of numbers, so don't worry about that. What else do I need to mention? Oh, yes. So you should all hopefully have had an abstract booklet. They were sitting on the table outside. If not, please grab one at the earliest opportunity. You will see that one of our speakers had to pull out at the last minute due to an unfortunate illness. So Randy Parrish, the last speaker in the day, has been replaced at very short and admirable notice by Claire Warren, who stood in and filled the void here. So she will give a talk at the end of the symposium. I think that's all the really dull stuff. Okay, so getting back to the scientific program, it's a huge pleasure and an honor to introduce, on behalf of the prize committee, the 2014 Crafoord Laureate Peter Molnar. Now, Peter started his work back in the early days of plate tectonics. It was really just a new theory then. Rigid plates were moving across the surface of the globe. We didn't know what was driving it. There was no driving mechanism for this. And some of Peter's earliest work involved looking at earthquakes in subduction zones and realizing that, in fact, a major part of the driving mechanism was actually the gravitational pull on the plates in subduction zones, whereas rather than the push from the ridges. So that was a very, very important early piece of work that Peter and his colleagues were involved in. But then Peter moved on, and he described himself to me recently in an email as a mountain man. He likes mountains. And it's very obvious that probably a mountain man is going to move into the mountains. So Peter saw a major problem in plate tectonics. Plate tectonics couldn't explain the kind of deformation we see in mountain belts, in major continent-continent collisions. It was just unable, with the theory of rigid plates moving over the surface, to explain things like the Himalaya, Tibet, the Alps, places where we have high mountains, rapid uplift, large amounts of deformation. And I think it's probably fair to say that pretty much the rest of Peter's career has been devoted to these problems, with a wide variety of collaborations and different methodologies being applied to the problem, and largely focusing on the India-Eurasia collision, which started 50 million years ago. So today, in our Mountain Belt Dynamics Symposium, we're going to hear presentations on a lot of different aspects of mountain belt dynamics. I'm sure there will be lively debate. Please don't feel that you have to be hold back too much. There's probably not a consensus on this. I'm sure there isn't a consensus on it, and we'd like to have some really, really lively debate going on. So, without further ado, I invite Peter to come onto the stage and give his talk, Mantle Dynamics, and the Rise and Fall of Mountain Belts. Thank you, Peter.
Thank you, Martin. Am I on? I don't. Okay. Well, thank you, Martin. I think it should be obvious that this is an extraordinary experience for me. and you don't want to listen to me just waste your time with all the thanks that I could give, so let's just move on. So I'm going to talk mostly about the Tibetan Plateau and its surroundings, and I have to understand how this works. Yeah. So the Tibetan Plateau, the Himalaya lies down here. This is, of course, the Indian subcontinent. I'll talk somewhat about the Tian Shan as well. And I'd like to start with an animation. This is made by Tanya Atwater, who's sitting here in the audience today. And I'll run this through a couple of times. But we have India to the south, Asia to the north. The lighter color in here is crust, an ocean in between India and southern Asia with thin oceanic crust. The hotter colors underneath show the mantle, with the darker part, the lithosphere, the strong part of the mantle. So let's just run this. Let's go. Okay, so let's just watch this happen, and I'll show you this again in a second. India plowing into Asia. Now, I want to look at this, and I want to focus you on a bit of it. First of all, before the collision, 40 to 50 million years ago, a high range bounded the southern edge of Asia in here, a range like the Andes itself, where you had volcanoes and somewhat thicker crust. The Himalaya has been built by slices of India thrust atop the Indian subcontinent. So when I show this again, watch this part of India. So you see India going north, a thrust fault in here, another fault, building a high mountain range in here. So the point here is that the Himalaya itself is built by pieces of the Indian crust, not by Asia. It's entirely the Indian crust here. And if we look at a modern-day cross-section through the Himalaya, looking southwest on the left, northeast on the right, this red rock over here is the southern edge of Asia. The green is showing you remnants of that ocean floor that was underthrust. And then this is all Indian rock on this side, where the current Indian crust is shown underneath this red line, being underthrust beneath the rest of the rock in here. The Himalaya consists of slices of the old margin of India, slices. It's built by the stacking of slices of India's crust on top. Okay, now let's look at this again. Since the collision, India's penetrated steadily into Eurasia, shortening and thickening the crust. So the Tibetan Plateau is going to be built in this area as India plows into it. And you might notice this area. This is the Tian Shan to the mountain range to the north. So if we run this again, India pushes in, you thicken the crust, many faults across a wide area. You get a big, thick crust in this area, thickened crust back in that region. And if we look at modern-day crustal thickness, indeed, Tibet has a very thick crust. A scale down here going from zero, there's no place with zero, going down to as much as 80 kilometers under the Tibetan Plateau. These are simple processes that we think we understand. Now, most of this talk is going to concern a much more speculative aspect of this. So I'm going to show you this one more time. This is where we disagree, and I've asked subsequent speakers to feel free to disagree. That will make it more interesting for you, I hope. But this time, watch this the mantle lithosphere, this colder region of the mantle in here as India penetrates in. As I said, this is a speculative idea. Could be wrong, but I've been working on this for many years. So you plow India in, this region thickens, and then you see a blob of it drop off down here, and the hotter material from underneath has intruded to the base of the crust in here under northern Tibet. As I said, this is how I'm going to focus all of this talk around that idea. Now, in simple terms, in simple non-animated terms, we know we have a crust on top, which is lower density than the mantle underneath, and in particular than the mantle lithosphere, the strong upper part of the mantle, which overlies a weak region, the asthenosphere, beneath it. And if you imagine you thicken this upper layer, so you thicken the crust, you build a mountain range or a high plateau that stands above the lower regions, there's a root of thickened crust underneath, but you must also thicken, you must do something with this mantle lithosphere, so we presume that it will thicken as well. Now this mantle lithosphere is more dense than the surrounding asthenosphere, so this is a weight, it's ballast on the bottom of the mountain range beneath, so it will pull the surface down a little bit in here. In addition, this colder material next to hotter material creates an instability where this thickened colder material will tend to sink and disappear. So let's just take it away. Imagine that that region disappears, and this lighter blue region is showing mantle material that has been removed, mantle lithosphere that's been removed and replaced by hotter material. So remove the blobs of dense mantle lithosphere, you take that load off the base, and the surface goes up. You give the whole region potential energy, available potential energy to atmospheric scientists, that is then capable of doing work on the surroundings. So the surface rises because you take this load off, you give it potential energy, and that can power an outward growth of the plateau and an extension within it. So we imagine in this later stage, the mountain range will tend to collapse. It will spread apart in the center, although there will still be faulting on the sides where the mountain range grows outward at this time. So how do we test this? Several possibilities. Lateral variations in seismic wave speeds and in density. If we remove this, we should have differences, lateral differences in that strength, in that material. We'll have enhanced volcanism because we've thinned the mantle lithosphere that's cold. We've brought hot material to shallow depths. We'd expect enhanced volcanism. We expect an outward growth of the range or the plateau out on the sides, and crustal thinning beneath the high plateau, thinning in this region, and an increase in surface elevation. When the load is removed, the surface goes up. You take the ballast out of a ship, throw it over the side, the ship comes out of the water. So let's look first. Seismic tomography. We'll use seismic waves to study the upper mantle structure and looking for high speed zones that would show where blobs are sinking. Now, to do this, we don't yet have enough data to look at this in the detail I would like to show you from the Himalaya, but from the Tian Shan, the mountain range across this northern region up in here, we can see this quite well. This is a mountain range that's been built largely since India collided, the same time that we built the Tibetan Plateau in this area. All of these dots show seismograph stations that were employed, most of them temporarily. I'm going to rely largely on this profile of seismograph stations installed by Chinese scientists, Stephen Raker, an American, and Russians working in Kyrgyzstan. So this is a map of the stations in the Tian Shan. If we look now just at the uppermost mantle, the P-wave speeds, P-wave traveling in the uppermost mantle, what we see, these two maps are the same scale. So here's our seismograph stations, and here these white dots are the locations of earthquakes used to study the upper mantle. We have a big region of low speeds, as low even as 7.5 or maybe 7.4 kilometers per second. These are very low speeds. Only in the surrounding edges do the speeds get up to 8 kilometers per second. Low speeds suggest high temperature. So the suggestion here is that the Tian Shan is underlain by hot material. Now, a cross-section made using that line of stations over here, shown on this profile, where north is to the right, south to the left, going down 100, 200, 300, 400 kilometers. Again, these same authors. What you see are two belts of high-speed material, perhaps as high as 2% faster than normal, on the northern side and on the southern side, beneath the edges of the Tian Shan. That's the northern edge, the southern edge of the Tian Shan. This high terrain is the edge of the Pamir, but most of this profile goes into low terrain down in here of the Tarim Basin. This high-speed material suggests that blobs of cold material are sinking into the asthenosphere underneath. Now, these authors carried out studies to determine how much of this image you should believe, and they will tell you, don't believe what's below 400 kilometers, just this upper part. Well, if we just cut it off near 400 kilometers, this looks very much like what one gets with numerical calculations that Greg Hausman and I carried out many years ago, where we have a crust that's low density, overlying mantle lithosphere that's a little bit more dense than the surrounding material. We shorten this horizontally. In fact, of course, we only looked at one side, and then I flipped this to give you symmetry. And for certain combinations of density and for viscosity, even though the shortening, the convergence, is all absorbed in this central part, drips of mantle lithosphere occur on the flanks. We have paired downwellings that look like what we have here. So we want to believe, especially since we did this work before they did theirs, that this is an example of drips of mantle lithosphere coming off the bottom below the crust where convergence has taken place. So seismic tomography with high speed zones. Lateral variations in density, lateral variations in speeds and density. Another way of looking at this. Now we turn to Tibet. We're going to look at the Tibetan Plateau. The next map will be of this region extending all the way to the Tian Shan. This again is P-wave speeds. Pn is the P-wave that travels just below the crust. This is work that's 20 years old. For this region where the crust is thicker, you can imagine that if the P-wave speed is greater than 8.1 kilometers per second, it's cold. If it's less, it's warm. And you can see this low-speed material in the north where we imagine it's warm compared to the colder region to the south in Tibet, the colder surroundings up here, higher speeds. And remember, this was a place in the Tian Shan where the previous authors had found low-speed material. Okay, another look at this, but using a different approach. In the upper left is a map showing where there's a line of seismograph stations over here, and I've made a guess at approximately where that line is across southern Tibet down here. And this is a little bit complicated. What they've looked at are S waves that are coming in to the bottom of the crust, so that's the base of the crust. The Earth's surface is up here. An S wave comes up to a station at the surface. But in addition, farther away, an S wave will come up, be refracted into the crust, and reflect off the surface as a P wave, reflect off the moho, the base of the crust, and reflect back to the surface. And for the right distances, this is a very strong reflection. This is a critical reflection where the P wave is a strong signal. So it's simple when you look at the seismograms. This is a collection of seismograms. Time increases downward. All of the seismograms at these stations are aligned along the S wave here so that the real times are different. If you're farther away, it's a little bit later. But they're aligned along the S wave. And then you have this stronger phase coming in later. That's this reflected phase that's come down, reflected as a P wave, and come back up. And clearly, the time difference between the direct S wave and this phase that's reflected here will depend on the thickness of the crust. Well, you can see that the time difference gets shorter as you go to the north, measured in time here, 0, 10 seconds, 20 seconds. If you convert that into a thickness, the crust in southern Tibet is thicker than it is in the northern part. And the difference is nearly 15 kilometers. That's 75 kilometers here, as few as almost as small as 60 kilometers in the north. This is a large difference, 15 kilometers between the north and the south. So if we combine these, we have low speeds, low P-wave speeds in northern Tibet, lower than in southern Tibet. That suggests we have a hotter upper mantle beneath northern Tibet. We have thinner crust beneath northern Tibet, thinner crust here than we have here. And if we combine that with isostatic compensation, Archimedes' principle, thin crust but a low density upper mantle beneath northern Tibet than southern Tibet, less dense upper mantle. So we have a density difference. Again, this is what we would predict if mantle lithosphere had been removed. So the idea passes this test made of it. So we've looked at lateral variations in density, speeds and density. What about volcanism? This is a map of young volcanism in Tibet. So we're looking not at the whole of the plateau, but a portion in this area, the Tarim Basin to the north. That's this basin in here. The yellow show the youngest volcanism. You can see 1 to 10 million years, 16, 14 to 9, different ages. They become older in the south, 45 to 33, 31 to 39. This young volcanism was studied many years ago, 20 years ago, by Turner. Oh, sorry. Yes, some pictures. Volcanism in northern Tibet. This is volcanic rock all over the place. Again, volcanic rock. When one goes to northern Tibet, only in the winter because it's mud, and you will be stuck in the summer, so you go in the winter when you can drive on frozen ground. You don't always have success, too. Sometimes you become stuck. But volcanic rock all over. This is all young volcanic rock lying on top of sedimentary, much younger sedimentary and metamorphic rock beneath. Now, work by Turner, 20... Is that me? No. Work by Turner many years ago looking at volcanic rock in northern Tibet, up in here. What they looked at was a bunch of properties of that rock. This is isotopic ratios of neodymium. Neodymium is an element that has two isotopes that allow it to be distinguished quite clearly. Strontium 87, 86, again, two isotopes of strontium. Crust typically has low neodymium isotopic ratios and large strontium isotopic ratios, whereas mid-ocean ridge basalt is the opposite, large neodymium, small strontium. This rock in northern Tibet is in the middle. And you might think it's a mixture of those two, but that's not the view that Turner had, and it's not the view that others would have. This is a sequence of images. This is potassium-rich volcanic rock. And what happens is potassium goes into the melt very easily. And so the Turner imagined, as would others, I think, that you had crust, mantle lithosphere, and little bits of melt that would seep in from the asthenosphere. That potassium-rich melt seeps into the mantle lithosphere in here to enrich it in potassium and enrich it in rubidium, which decays to make strontium-87, and in other elements. Then you thicken this crust and mantle lithosphere. You thicken the entire lithosphere. So the crust becomes twice as thick, the lithosphere becomes twice as thick. And then you remove the bottom part of the mantle lithosphere. The lower lithosphere is removed, and that heats the overlying potassium-rich material, heats up this material that's rich in potassium, rich in rubidium, and other incompatible elements, which lower the melting temperature, and that rock then erupts at the surface. This is their image, which, of course, I share because it's consistent with what I'm telling you. So we've talked about volcanism, changes in style of deformation on the flanks. Now, this slide, you cannot possibly digest all of it, but this is a map showing Tibet in the middle and showing places all around the edges where there's been recent deformation. Recent in the sense that the collision between India and Eurasia occurred 40 or 50 million years ago, but this is deformation that's younger than 15 million years. The Baikal Rift opened 10 to 7 million years ago, and then all around the flanks, you can read these numbers, 8 million years ago, 13, 10 and a half, 8, and so forth, along in the Tian Shan. Now, I should tell you, nearly all of these cases, what one is measuring is not the time of deformation, but the time of some other phenomenon that we think records deformation. So suddenly, around the flanks of the Tian Shan, there's an abrupt increase in sedimentation, an abrupt increase in coarse sediment. So the inference is that the mountain range rose to become higher and then eroded quickly. But I'm going to show you a couple of examples of data from this region. The first one I'm going to do is show you south of India, down in this area. Here's India, Sri Lanka, and we're going to look at a profile, a seismic profile across this region. So on the bottom is the profile. You see the floor of the ocean. You see a little peak sticking through, but this is sedimentary rock. You see layers of sediment. You see a little peak sticking through here, coming across a bigger peak. Again, sedimentary rock in here. You see a hint of the basement below the sediment coming up, and then a big high over here. Above are gravity anomalies. The gravity anomalies become positive where rock that's more dense than the sediment sticks up. So the peaks in the gravity field are all standing over the high areas and even over this area. Note the scale, 100, 200 kilometers. This is long wavelength, small strain. This, for those of you who care, is a profile of the geoid, the equipotential surface, the deflection of sea level, if you like. So long wavelength feature. This was drilled by the Deep Sea Drilling Project. Now, we've changed the scale. This is 5 kilometers here. And these are all sedimentary layers. Each of these lines marks a contrast in the sediment so that you get a strong seismic reflection. And what you can see is some of these layers are warped over the top of these folds, and some come in and just lap on top. Obviously, the ones that are all warped predate the folding. Those that lap on top postdate the folding. And Jim Cochran, years ago, found that this layer A in here marks the boundary between the layers that are folded coherently and the layers above that lap onto the folds. And the date that was given is 7.6 billion years. Revision of this makes it a little bit older. But the point is that this folding accelerated, it may have begun a little before this time, at about 8 million years in this area. Okay, I'm going to switch now to the Tian Shan back up here and take you through another argument. This is results of GPS measurements, measuring active movements. The Tarim Basin lying down in here, so we're looking up in that area, Tarim Basin. These arrows are showing you motion of points measured with GPS. There's a scale, 10 millimeters per year here. So this is 20 millimeters per year of this region relative to Siberia to the north, with deformation across the Tian Shan. This is fast. 20 millimeters a year is very fast. In fact, the convergence between India and Eurasia at this longitude, India moves north relative to Eurasia at only 35 millimeters per year. So more than half is absorbed in the Tian Shan. I insist that that's a high rate. Moreover, the total north-south shortening in this region is no more than 200 kilometers. 200 kilometers to build the Tian Shan. It's probably even less than that. And if you take 200 kilometers, divide it by 20 millimeters per year, which is the same as 20 kilometers per million years, 10 million years. It takes only 10 million years to make the Tian Shan. The Tian Shan probably are a little bit older than that, but most of the mountain building, most of the shortening has taken place in the last 10 million years, long after the collision between India and Eurasia. I'm going to take you to the northeast edge of Tibet up in here. This is the Chilian Shan, the high mountain range at the edge of Tibet, work of Jung Do-won, Maureen Clark, and colleagues. And what they've done is they've looked at rock along the edge within a piece of old granite, Paleozoic granite, that's been thrust atop younger sedimentary rock on this side, and they took samples at different elevations in here and measured the ages using uranium, thorium, helium, which tells you when the rock cooled below about 70 degrees Celsius. And plotted here is the elevation of the rock, 1,800 meters, 2,000 meters, going up to 3,400 meters, and the ages that they got, 20, 40, 60, going out to 200 million years. And what you see is a long elapsed time between cooling of this rock when the rock is a different elevation of only 400 meters. Slow cooling. What's happening is rock is being removed from the top, you're eroding rock off the top, cooling the rock at greater depth, and this happens slowly between 180 and 20 million years ago. And then you see this precipitous drop, rapid cooling starting near 9 million years ago. So the inference is that this block of granite has been thrust on top of the sediment beginning about 9 million years ago. Thrust up here, and then erosion stripped this rock, rapidly cooling first the rock near the top, and then cooling the deeper rock as erosion took this away. Another example, way out to the east of Tibet, in the Liupan Shan, again, approximately 8 million years ago, and again, Jung Do-won and his colleagues. This is a map of the region with a profile, with a cross-section through here. Look at this cross-section. Most of this is Cretaceous rock between 70 and 130, 140 million years. They took samples across here. There is a thrust fault dipping underneath here where this rock has been thrust upward on top of the rock on this side. If you plot age, again, starting 140, 120, 100, back to the present, the red shows you the age of the sedimentary rock. The bottom is older. That's no surprise. You bury the rock. But as this rock was buried, it became warmer. And as it became warmer, it destroyed the record of damage due to radioactive decay. Fishing track ages are telling you when the rock cooled below approximately 120 degrees Celsius. So what you see is burial. That's this younging as you go up. And slow warming until about 100 million years ago. So this rock warmed a little bit after it had been buried. And then, note this really abrupt change there, beginning about 8 million years ago, suddenly very abrupt cooling. So the presumption is that this layered sedimentary sequence was thrust atop this region about 8 million years ago, and then erosion stripped this rock, cooling the rock underneath it. So the image that we have is that northern Tibet became higher, and then this exerted a force on all the surrounding regions, surface rose, and the outward force per unit length, then increased, caused deformation in the Tian Shan, caused deformation around the flanks, caused accelerated deformation within the Himalaya, and even deformation down in the Indian Ocean in that area. So we've had a change in style of deformation on the flanks. Now let's look within Tibet, a change in style of deformation where we have normal faulting, horizontal extension, and crustal thinning. First, GPS from Dongpei Jun. He'll be talking later this morning, or this afternoon. These are GPS measurements of India and Tibet, Tarim Basin, relative to Siberia. All of these are relative to Siberia. You see Tibet being squeezed out to the eastward and flowing around the corner of India. But what I want you to focus on are these arrows. These have an eastward component where these do not. These are more northward. This is showing you that you have east-west extension within Tibet today. The divergence of the arrows in here compared to those over on that side. And we see active faults, or recently active faults. There's a fault here where this sedimentary rock has been dropped down relative to older metamorphic rock on this side. This is in northern Tibet. Well, if we study the earthquakes, for those of you who know this diagram, these are lower hemisphere diagrams, lower hemisphere projections of the strain field. But in simple terms, the ones that are red show crustal shortening, in this case, underthrusting of India beneath the Himalaya, crustal shortening out in here. The red area in the center is showing you that you've had vertical extension. The white areas on the surroundings, on the margins, are showing you that the surroundings are coming toward one another. The blue symbols in the middle show normal faulting and crustal extension. So if you look at that one as an example, the blue on the side means that you have roughly east-west extension, and the white in the middle is telling you that the layer involved in this is becoming thinner. So we have normal faulting, east-west crustal extension, and thinning throughout Tibet. At the same time, thrust faulting, crustal shortening on the surrounding flanks. And if you plot these, as Elliott and his colleagues have done, as a function of the elevation above the earthquakes, the normal faulting is in the high area, with one exception, this one down here, which is due to a flexing of the Indian plate as it bends down, and thrust faulting on the margins. The thrust faulting showing you that the plateau is growing outward, the normal faulting showing you that the plateau probably is dropping in elevation and extending in an east-west sense. So we have a simple image of this. This was drawn actually by Jane Silverstone for the Alps, but we think of Tibet as being like one huge piece of camembert or brie cheese spreading. As you take the walls aside, it thins in the middle and spreads out on the flanks, spreading onto the Indian plate and onto southeast China. Well, a second fact that we must take away is this crustal extension in the plateau is not how you build a plateau. You build a plateau by the phenomena that's taking place on the surroundings out here, by this thrust faulting. This requires a change in the balance of forces, strictly per unit length, that are holding the Tibetan Plateau together. There's been some change in the development of the plateau, where the plateau now, instead of growing higher and being thickened by thrust faulting, it is now extending in an east-west, with an east-west orientation. And we can ask, when did that happen? What's the onset of rapid east-west extension of the plateau? And the answer is, it's since approximately 15 to 10 million years ago. If you look at these numbers, this is the youngest, 7 to 5 million years ago, 8, less than 12 and a half, 13 to 12, and so forth, coming around 13.5 for the one in the northernmost part of the plateau. We need to get dates farther north, of course. But the point is that, again, there's been a change at approximately the same time when we see this big acceleration of deformation in the surroundings of the plateau. And if you take the present day rate of extension determined from GPS and assume that that rate has applied for the last 10 to 15 million years, you extrapolate that present day rate for that amount of time, this gives you a drop of 500 meters in the mean elevation of Tibet. We infer that Tibet is now in a state of collapsing. It's going down, the elevations are becoming lower, and not a big drop, only 500 meters in the last 10 to 15 million years. So we have now changes in style of deformation, normal faulting, crustal extension, crustal thinning. What about paleoaltimetry? In the last 25 years, there's been a big acceleration in trying to determine quantitatively paleo elevations. All of the work shown here is, in fact, 21st century work. These are places where people have gone and made estimates of past elevations. So the first one of these with Carmela Garzioni, where she and her colleagues went into this area, looked at rock 11 to 10 million years ago, examined a couple of places and inferred past elevations of 4,500 to 6,300 meters. Uncertainties are still large in this. That's no different from present-day elevation. In fact, all of these inferences of past elevations, with one exception, look no different from today's, including some that are quite old, 26 million years, 35 plus or minus 5 million years ago. And even the authors of this paper, I think, agree that this is not a reliable estimate. So everything suggests no change in paleo elevations since perhaps as old as 35 or 40, even 40 million years ago. Now, this is inconsistent with what I'm telling you, but let me give you a reason for doubting this. All of these measurements, with one exception, with Spicer's work in this area, all of these are based on oxygen isotopes, oxygen-18, in carbonate sediment deposited in the ground, where the oxygen-18 is inferred to come from rainfall, and oxygen-18, the oxygen-18 in the rainfall will be much more depleted when you have high elevations because it's precipitated out as the moisture rises. So what Bershaw, Penny, and Garzioni have done here is they've taken a site, this is the outline of Tibet, here's a site in southern Tibet, and they've calculated where the water comes from when there's been a rainstorm in this area using modern meteorological techniques. And in southern Tibet, the rain comes from the south. And this is what you probably would expect, and when you drew paleo elevation inferences, this would be what you would expect. In theory, would say you could use this to make a good estimate of the elevation. If you're in northern Tibet, however, the rain came from the north. We know nothing about where that moisture started. We can't be sure. And in the middle of Tibet, half the moisture is from the north and half is from the south. Well, if we go back 40 or 30 million years ago, we don't have a clue where the rainfall came from. In southern Tibet, it surely came from the Indian Ocean from the south. So southern Tibet, we probably can have reliable inferences of paleo elevations. So to give you a bit more about paleo elevation and to support what I'm saying, but not from Tibet, I take you to the Andes. This is a map of the central Andes, Bolivia in here, Peru to the north, Chile, Argentina. The white shows you high areas, 3,800 800 meters or higher. The purple is even higher, above 3,800 meters. And although paleoaltimetry from Tibet offers no support for removal of mantle lithosphere, I'm going to offer the Andes as a place where maybe it does. Simple cross-section across the Andes, west on this side, east over here. The Nazca Plate underthrusts beneath the Andes at approximately 60 or 70 millimeters per year. Concurrently, the Brazilian region, the low Brazilian shield, underthrusts westward beneath the high Andes in this area. This red indicates a place where we think mantle lithosphere has been removed. So we have a similar situation to what we're saying about Tibet, except it's a somewhat different setting. Estimates of paleo elevation, this is Carmen Garzoni's work, I've forgotten his name, Josh and Kate Gregory. 3 different approaches, oxygen isotopes, the same approach that I was talking about with Tibet in the blue, suggesting low elevations back, here's the scale, present day, 5, 10, 15, 20, 25 million years ago, low elevations below 2,000 meters before 10 million years ago, and then the oxygen isotopes suggest a rapid rise. Paleobotany, this looks at leaf shapes, and how they've changed leaf shapes and sizes, how they've changed, Kate Gregory's work. She has low elevations between 15 and 20 million years ago, and again, quite low elevations at 11 million years ago. No more recent data. And then this delta 47 oxygen isotopes, this is a term that really means estimates of past temperatures using clumping of oxygen and carbon isotopes. Delta 47 is a measure of the clumping in a carbon dioxide molecule of a carbon 13 and an oxygen 18. This allows you to make an estimate of temperature, and temperatures that have become lower, hence an increase in elevation between roughly 11 million years ago and 6 billion years ago, and then present-day elevation. So this is saying that the central Andes rose rapidly since roughly 10 million years ago and had risen high by 6 or 7 million years ago. Well, if one looks in the Andes at the history of deformation across them, this is a breakdown, German scientists, Elger, Onken, and Glodny, breaking the Andes into different parts. The pre-Cordillera here is the western edge along the edge of the Pacific Ocean over in here. The western edge, what's plotted is the shortening rate, 1, 2, 3, 4, 5, 6 millimeters per year, going back 10, 20, 30, 40, 50 million years ago. The pre-Cordillera, most of the deformation in the pre-Cordillera was between 35 and 50 million years ago. The most active region, the eastern Cordillera, lying just at the edge of the white over in here, this is where most of the deformation had taken place in this period, spans this whole period from 45 to 10 million years ago. And then a breakdown of the eastern Altiplano, the high area, central, western Altiplano, different periods of time. The real reason I show you this picture, though, is, look, nothing has happened since roughly 10 million years ago. All of this deformation, which is in the high area in here, stopped at about 10 million years ago. Well, what happened 10 million years ago? If we blow up the Andes, there are ridges in here, ridges all along the eastern side of the Andes. These ridges mark folds in the sedimentary rock on the eastern side, and all of that deformation came since 10 million years ago. Deformation has occurred on the eastern flank of the sub-Andes since 10 million years ago, and therefore, again, we have outward growth of the belt. The belt became wider at 10 million years ago. And that's consistent with this change. The Andes grew outward to the east when the Altiplano rose. Okay, so to summarize, using this illustration, if we imagine we have low-density crust overlying more dense mantle lithosphere, overlying slightly less dense asthenosphere, and we thicken these two, we make thicker crust, but we also make a thicker mantle lithosphere. This is cold material. It's therefore more dense than the surroundings. It's a weight, pulls the surface down a little bit. But this is also an unstable situation. If we remove this, so this shows where we remove material, the surface should go up. This material goes away. We put potential energy into the system surface rises, and then this available potential energy can power outward growth of the plateau and crustal extension within it. So we switch to that state there. And I've argued that we see the evidence of this. Lateral variations in speeds and density, seismic wave speeds and density, enhanced volcanism, outward growth of both Tibet and the Altiplano, or the Andes, crustal thinning beneath high Tibet, and increase in surface elevation. Well, I want you all to know that it's been a great life. Studying mountain ranges has given me a good life, and thank you, Crafoord Foundation and Royal Swedish Academy, for confirming this fact with extraordinary generosity. Thank you.